So today we are moving to a new topic. Until now, at least the last several lectures were on unsupervised learning. For those who remember, we started and in fact spent much of this class, I would say 40%, on supervised learning. We then moved to unsupervised learning, which was clustering and dimensionality reduction, very important topics. And now we are moving to a new topic, which we will spend a few weeks on and maybe later come back to. And that is a topic related to joint probability distribution representation, uncertainty, and how to model the relationship between things. And you can use this, of course, to do supervised learning and to do inference, but that's not the only thing that you can do. There's more things that you can do with these things. So this is basically a way to represent our assumptions and our beliefs on the world and use these to either do classification if you want, or to do something called inference, which is to infer values of things that were not observed, okay? So the topic of today's lecture, and in fact the topic of this whole module, I would say, is graphical models. And within graphical models, there's a bunch of, and the name will become clear hopefully in the next few slides. Within graphical models, so you can think of graphical models as a family of methods, and within, for example, like neural networks, right? So we talked about feed-forward neural network, you know, convolutional neural network, recurrent neural network, so forth. So similarly, graphical models is a large family of methods. Within this family, there are lots of different subtypes. The first and the one we will spend the next two lectures on is called Bayesian networks. We will also discuss other members of this family, including something called hidden Markov models, but we won't discuss all members. So you should know that even though we are only spending 4 lectures on this, there is an entire class you can take. I think Eric is usually teaching a class every other year on graphical models where you spend the entire class on variants of these. Okay, so but today we're going to talk about graphical models generally, and within graphical models on Bayesian networks. Okay. So what is the whole idea of graphical models? Why are they useful, and what are we using them for? So graphical models are basically a way, and there's different ways of doing it, but the general thinking is they're a way to bridge the gap between two extreme methods we discussed in class already. The first extreme method is this method of fully dependent set of variables, right? We call this joint probability distribution. If we want to compute the probability of A, B, and C, we can write P of A, B, and C, right? That's the joint probability of the A could be 1, B could be 2, C could be 1, something called the joint probability distribution, right? And we said that, you know, we can compute it. Let's say A, B, and C are binary variables. We can compute it, but in order to fully represent this distribution, we need a lot of parameters, right? If we have 3 binary variables, we need 7 parameters, right? Because they have to sum to 1, but 2 to the power of 3 minus 1 parameters, right? We need to estimate, which may or may not be a lot. On the other extreme, we talked about complete independence or conditional independence, and we discussed it when we talked about naive Bayes, for example. In complete independence, the probability of A, B, C, the joint of A, B, C, is the probability of A times the probability of B times the probability of C. In that case, we only need 3 parameters because we only need to estimate parameters for A, B, and C separately. So these are the two extremes. It turns out that there is something in between these two extremes that on the one hand does not require us to use as many parameters as the fully joint model, but on the other hand does not assume fully dependence. So in some sense, it's a way for us to introduce some belief about the relationship between these variables in order to reduce the space of parameters without sacrificing accuracy, because we already said that if we can always assume independence, obviously, but this will come at the expense of accuracy. That's why naive Bayes is not one of the top classifiers. The assumption is too strong. That's why, for example, decision trees or variant of decision trees that do not assume independence do much better. So graphical models are a way to bridge between full dependent models, which are great, but usually impossible to learn because they require too many parameters and a lot of data, and fully independent models, which are bad for real estimation, but are very easy to learn. Okay, so that's the basic idea. right? And again, that's what we said. If we have 3 binary variables, we need 7 parameters. If we have 10, we need 2 to the power of 10 minus 1, which is huge. So graphical models are basically a way to bridge this gap. Okay, so why are they called graphical models and what do they do? So graphical models and Bayesian networks, graphical models are a set, as I said, are a family of methods. They are all represented by graphs. Graphs means that we have nodes and edges. Different graphs or different members of this family will have different meaning for the edges and the nodes. Usually nodes will represent random variables, but the edges will represent different things. So in this lecture, we are going to talk about one of the members, a very important one, but still one of the members of this family, which is called Bayesian networks. Okay, so let's discuss what is Bayesian network and explain the graph structure of Bayesian network. So in Bayesian networks, we have 2 main components. There's another one we'll get to in a second, but 2 main components. One are nodes. You can see here nodes. And the second are edges, okay? Nodes are the random variables in our model. For example, this is a setting I mentioned already. Let's say I want to learn a model about whether I will sleep in a movie or not, okay? Not really whether I sleep, but some joint distribution of 3 possible values. The length of the movie, whether I like it, and whether I slept in it, okay? So there are 3 random variables. You know, how long, maybe more than an hour, less than an hour, whether I slept, which is, let's assume all of them are binary. So these are random variables, right? They can take the value of 0 or 1. And there is a relationship between them. So they are not independent. Obviously, if the movie is very long, it's more likely that I slept, if I didn't like it, and so forth. But they might not require a full dependence assumption. So this is an example of a set of variables that can be represented with a graphical model. So the graphical model takes each of these variables and represents it as a node, right? Length, slept, and liked. Each of these is a node. And then we have edges. Edges represent dependency assumptions. It's not necessarily, and we'll get, that's actually a bit delicate or not trivial issue to explain exactly what is the dependency assumption that an edge has. But for now, and we'll get to a more formal definition, an edge between 2 random variables indicate dependence between them. The lack of an edge is a strong statement. It means that given the other edges, they are independent. Not completely independent. They might still be dependent, but if we know something about the other edges, they are independent. So in this case, for example, the interpretation is that whether I slept or not will depend on the length of the movie, and whether I like the movie or not will depend, and whether I liked it will also depend on the length of the movie. But right, if I don't know anything about the length, these 2 are independent. Sorry, if I know the length, these 2 are independent. Okay, we'll get to that in a second. But generally speaking, again, I don't want to go into the exact details of what the edges mean. We'll get to that. But I just want to mention that, again, the nodes are the random variables and the edges are related to dependency relationships. Again, if you have any question, any comments, if you want to raise your hand, please write to the chat. Daniel agreed to monitor it and alert me and stop me. Okay, that's something that, okay, so this is a Bayesian networks. Bayesian networks, and again, that's not true for all members of graphical models, but specifically for Bayesian network, that is true. Bayesian networks are graphs, so they have nodes and they have directed edges, so the edge has a direction, and they are acyclic. Acyclic means that we do not have a cycle. So for example, we cannot have an edge. So this is a valid Bayesian network. It has 3 variables, A, B, and C. It has some directions. This is a valid Bayesian network, okay? But this one, is not a valid Bayesian network because it has a cycle, okay? So Bayesian networks are not allowed to have a cycle. And we'll get to in a second, or we'll get to later why this is very useful and why this is a requirement for Bayesian network. But it's definitely an important, and oops, sorry about that. But it's an important requirement, and we'll see in a few slides why this is useful. Okay, so this is the meaning of the graph structure of Bayesian network. So we have nodes that represent random variables. We have edges that represent dependency relationships, and then we have something else, which is called conditional probability tables, or CPTs. CPTs define the probabilities that are related to the edges. So, for example, length does not have any incoming edges. That means that for length, we just have a prior. It doesn't depend on anything else. So there is a prior. In this case, let's say some of the movies are long, half the movies are long, and half the movies are short. However, if you have an incoming edges, then your probability is a function of the nodes that have an outgoing edge to you. Or, in other words, in Bayesian network terminology, of your parents. Any node that has an edge going to you is one of your parents, and your probability, or the model that we create for you, is a function of your parents. In this case, S has one parent, LE, so we have a probability of S equals 1 given LE, and the probability of S equals 1 given not LE. The probability of S equals 0 is 1 minus the probability of S equals 1. But these two do not have to sum to 1, right? Because these depend on the parent. Similarly here. If we had two parents, so for example, if instead of this model, I would have an edge going from S to Li, then Li would have two parents. In that case, I would need more entries in this table. That's why it's called the conditional probability table. So it's not necessarily a line. Again, if we had right, so in this case, B has two parents, so we need the probability of B has to be conditioned on has to be conditioned on its two parents, which is A and C. And so in that case, we need a four-way table, right? So this is P of B given A and C is basically P of B. In this case, P of B equals 1. We need to have basically four possible combinations, right? 1, 1, 1, 0, 0, 1, 0, 0, and for each one we have a probability. So this could be 0.2, 0.6. They don't have to sum to 1, obviously. 0.7 and 0.1. Okay, so this will be a table basically, and these are the values of the parents, and this is the probability that B is 1 given that this is the value of the parents. Okay, and if we have, I mean, the number of entries in the table, of course, is exponential function of the number of the parents. Okay, so this is a Bayesian networks. Well, this is the terminal or the language in which Bayesian network is defined. Again, nodes represent random variables, edges represent dependency or conditional dependency, and we have these conditional probability tables, CPTs, that define the probability of a node conditioned on the values of its parents. Okay, so far we just defined some notations in terms of graph. Now the big question is, how is this related to joint probability distributions? Okay, that's what we wanted to basically represent. In Bayesian network, it turns out that the joint probability distribution defined by a Bayesian network is just a product of the value of each node conditioned on its parents. So specifically, if we want to know the joint of three values, we have the product of each node conditioned on the product on the value of its parents. This is the joint. So in this case, we have the probability of LE, it doesn't have any parents, times the probability of LI times LE, the condition on LE, times the probability of S condition on LE. Okay, so this is the definition of a joint probability distribution defined by a Bayesian network. Basically, it's a product of each node condition on its parent. If it doesn't have a parent, then just a prior. If it has multiple parents, then this would be this would be a function of all the parents, all the values of the parents. But this is the joint probability distribution. Now, we said that if we assume fully independent model for 3 random variables, we need 3 parameters. If we assume fully dependent model, we need 7. How many parameters do we need to define the probability of this table, of this Bayesian network? Anybody? Let's check. So, Right. So as people said, and in fact, that's something you can see in the slides, we need 5 parameters in this specific case. And these 5 parameters are enough to define any joint. So 1, 1, 0, 1, whatever, right? Any value of the 5 different variables, we can get the joint probability using 5 parameters. And the 5 parameters, as I said, are actually defined on the slides itself. And so basically, we need 2 parameters for right. We need 2 parameters for S, 2 parameters for Li, and 1 parameter for E. So in some sense, we saved, rather than for having the full joint, we went from 7 to 5. On the other hand, we didn't sacrifice anything, because our idea is that if we know the value of Le, I can compute it's enough for me to know the probability of S given Le. If I know Le, I don't need to do the full joint, okay? And again, this will become hopefully, in some sense, let me explain this in a second, and then hopefully this will be. So why is this so useful? Okay, so we know that the joint we can always factor, right? Using the chain rule as P of Le, P of let's say Li. So we can always factor it, right? That this is P of Le. So, this is P of Li and S condition on Le times P of Le. That's true for any 3 random variables. That's not related to the network or something. Now this is a P of Li condition on S and Le, P of S condition on Le, P of Le. Right, this is true for any 3 variables. Okay, so this, of course, we know because this is true for any, this requires 7 parameters. Why? This part here requires 4, this requires 2, and this requires 1, so a total of 7. What did we gain from the Bayesian network? From the Bayesian network, we gained the fact that if we condition on Le, Li is independent on S. This is encoded as part of the Bayesian network. This is where we save. But it's not changing the accuracy of the joint. This is some of the assumption that we make, that if we really know Le, then Li is independent of S. So in some sense, we get the correct joint, but we still don't need to estimate as many parameters. That's the advantage of Bayesian network. So in other words, if you have a good and strong assumption about dependencies and independencies, but you don't have to assume that everything is completely independent. If you assume partial dependencies or just something that is dependent on other, if you know, and again, we'll give some stronger definition soon, then you can save parameters without helping your ability to fully find the joint distribution or correctly find the joint probabilities. So that's the advantage of Bayesian network. Okay, so given this, the question again, of course, is if we have a problem, how do we construct a Bayesian network? or how should we go about constructing a Bayesian network? So there's a simple algorithm. Again, I mean, it's simple to say. It's much harder to actually, or it sometimes could be hard to do it in practice. But the basic idea is the following. First of all, you identify the random variables in your domain, right? So in our case, we had 3. You can think of other cases, but definitely you need to identify the random variables in your domain. Then there's 2 options. One is to manually construct the dependency table. If you don't have a lot of variables, and you know about your domain, you can just do it, and I will show you an example in a second. And once you have the network, you can populate the conditional probability table. The conditional probability table, once you have the structure, is very easy to populate. How do we populate the conditional probability table if we have the structure? Anybody can give me an idea? Which algorithm should I use? If I have a structure and I have training data, obviously, and I want to populate the conditional probability table, anybody can give me an idea? So Bayes rule is something we use for inference, but for this is more learning. It's not inference. Yeah, MLE, right? So basically, this is simple MLE, simple probability distribution, right? We want to learn the probability of A given B or A given BC. This is exactly MLE. So if we know the structure and we have training data, it's very easy actually to compute the CPTs. The challenge, of course, is that in most cases, we don't know the structure. So now the question is, how do we learn the structure? In this class, we will assume that we construct the structure by hand. In practice, there are algorithms that can learn the structure. That's not trivial to do. In fact, you will see in a few slides that it's very hard to do. But there are algorithms that learn the structure, and with some sort of an EM algorithm. EM is something you discussed in the clustering method, in the clustering lecture. So you can use it here as well. For this class or for this 701, we will assume that the network is constructed by hand, okay? But even constructing by hand is not trivial. So let's do an example of a network that we can construct by hand and see what do we gain from using Bayesian network rather than just representing it as a full joint. And the reason why we bring this example is because this is the example that the person who, I don't want to say invented, but definitely popularized Bayesian network, a guy by the name of Judea Pearl, who won the Turing Award, I think 10 years ago, 15 years ago. That's the example, that the canonical example he gave. So we usually at least explain it in the first time we show Bayesian network. It's a very simple one, but hopefully intuitive. So basically, in this case, we have 5 random variables. B is whether or not someone broke into our house. E is whether an earthquake occurred. A is did the alarm sound. And then I have 2 neighbors. So I'm at work. The setting is I'm at work. You know, I have an alarm in my house. This is LA. He's in UCLA, so earthquakes are pretty common, probably. Burglaries are also common, so this is not Pittsburgh. I tell my neighbors, Mary and John, that if they hear the alarm, they should call me and I will come home and see what happens, right? I mean, or maybe if it's a burglary, I want to come home. If it's an earthquake, what can I do? But anyway, so there's 5 different random variables. Of course, they're not independent, right? Because if there was an earthquake, it can trigger the alarm. Of course, if someone broke into my house, it can also trigger the alarm. If John calls, it's likely that the alarm sounded and so forth. So this is the set of random variables. And I would like to do inference, right? For example, if John called me, I would like to know whether someone broke into my house or whether it was an earthquake. If it was an earthquake, maybe, you know, it can wait. But if someone broke into my house, maybe I should get there and call the police or something. Okay, so this is the setting. So the question is, how do you construct this network? So as we said, we can always use the chain rule to construct a joint probability distribution for this. And this is true for any 5 random variables. We don't need to know anything about them. We will get this joint probability distribution, right? Everybody hopefully agrees with it. This requires, because we have 5 random variables, it requires 2 to the power 5 minus 1. So basically 31 parameters. And you can write it as a Bayesian network, right? Because we said each one of these is a node depending on the set of parents, right? So A, B, E, J, and M. And this is a valid Bayesian network. You can see it's directed. It doesn't contain any cycle. So this is a valid Bayesian network. However, this Bayesian network does not contain any domain knowledge. So it was not constructed with only knowledge. So it contains a lot of parameters, 31 parameters, 2 to the power 5 and so on. On the other hand, if you do know something about the domain, you can set the Bayesian network as follows, right? So basically you have B and E are the two events that trigger everything. A is the alarm, which only depends on these two, right? The alarm doesn't depend on whether John called. The alarm, of course, if I know that John called me, it tells me something about the alarm, but the alarm only depends on whether someone broke into my house or else. And John calls me and Mary calls me because of the alarm, right? I mean, they don't know that someone broke into my house. Let's say there are, two houses away. They can't see my house. Yes, they can feel the earthquake, but the assumption is that the earthquake is limited to my house only. So they will only call me if the alarm sounded. Okay. So this is again the same joint probability distribution. So any joint that I compute on the 5 variables using this structure will be perfectly correct. So it will give the right, if I know the parameters, it will be the same as the joint that I compute using the previous network, which was fully connected, right? This is the only difference is that here I'm using information that I know about the domain. For example, I know that A is a function of A and B, whereas in the previous network, I didn't assume anything about the domain. Okay, but the saving is great because I get the fully correct, right? Any joint probability distribution that I compute using the parameters of this network is correct. It doesn't, I mean, it's not making any relaxation assumption like naive Bayes, right? Which assumes independence. I'm not assuming any independence. I'm assuming all the real dependencies, but I only need 10 parameters. Okay, so this is the advantage of Bayesian network. You can represent joint probability distribution correctly, but very efficiently. You only need very few parameters. And when I say represent, basically you also have to learn these parameters. So you have to learn much fewer parameters, which means that you need much less data, right? In the previous example, we had a node with 4 parents in this case, right? So even just for this table, we have 15 different parameters. We need a lot of data. In this one, which is again the same joint probability distribution in terms of accuracy, only the one with the largest one has 4 parameters. This is A. So we need much less data and we can get the same accuracy. Okay, so by relying on domain knowledge, we save. So again, as I said, in order to learn a Bayesian network, the first thing we need to do is identify the random variable. In this case, we set 5 random variables. The next thing is we need to create the network. Creating the network could be done either by learning, doing some automated learning, or by hand, okay? In order to do it by hand, you have to select an order, okay? And then add the information based on the order. It turns out that the ordering you select is critical. For the same assumptions that you know, so even if you have the same domain knowledge, if you order the nodes that you add to the network differently, you will get a very different structure. Again, representing the same correct joint probability distribution, but with much more or much fewer parameters. So let's do an example and show why this is the case. So let's look at a problem, right? So I have to order the parameters, right? So I have alarm, burglary, earthquake, John call, Mary call. Okay, so let's say we start with the burglary. Obviously, if I only have one node in my network, I don't need any edges. Okay, now I add the earthquake node. Does knowing that someone broke into my house tell me whether there was an earthquake at the same time? The answer is no, right? I mean, the fact that someone broke into my house could just accidentally be when the earthquake occurred, but it could, I mean, it's unlikely that the burglars knew something about earthquake, right? Most people, I mean, if they knew about that, they shouldn't break into houses. They can just create a new company that predicts earthquake and they'll be much more famous and much richer. Anyway, so there's no relationship between, or there's no dependence between B and E. So knowing something about B doesn't tell us anything about E. Okay, now let's add A, the alarm. Does knowing that the earthquake happened tell me something about whether the alarm sounded? Obviously, yes, right? If the earthquake happened, the alarm may have sounded. Now, if I know that an earthquake happened, or if I know something about earthquake and now someone tells me that a burglary happened, does it tell that the earthquake didn't happen, let's say, and someone told me that the burglary happened, does this add information about whether the alarm happened? The answer is yes, right? Because if the earthquake didn't happen, but the burglary happened, I would still predict an alarm. So even though I have this edge, I still need this edge. Okay, so that's it. I mean, I connected it to these two. That's it. Now I'm adding John called. Let's say that John called. Which variables that I already have is John called dependent on? So obviously, John will call me if earthquake happened or burglary happened. But he will only call me if he hears the alarm. So if I know whether the alarm happened or not, it shields me from these two variables. So if I haven't had A, I would connect it. But because I have A, I only need to connect John to A. Okay, this is the thinking, that if I know A, everything else is independent of whether John called or not. If I didn't know A, no. But if I know A, and similarly for Mary, so this is the model that we get, right? So this is nice, and this is because we started B, E, A, J, and M. But if we change the order, things may look very different. So let's start with John, okay? Let's start with J. Of course, this is the only one. We are not connecting it for anything. Now let's add Mary. If John called me, if I want to know whether Mary will call me, does knowing whether John called me give me any information? The answer is yes. Why? Because John likely called me because he heard the alarm. If John heard the alarm, maybe Mary also heard the alarm. So if John called me, it tells me that Mary likely will call me as well. She doesn't have to, there is probabilities, but if I know that John called me, then this is okay. Good. Now, let's add B. If I know that John and Mary called me, does this increase my probability that someone broke into my house? Yes, right? They would call me because of the alarm. The alarm would sound likely because of burglary. So obviously, these two are important to me. Okay, now earthquake. Earthquake, obviously, same reasoning for this, but also should be related to B. Why? Because if the burglary didn't happen and John and Mary did call, then it's more likely that earthquake did happen. So knowing that John and Mary called is not enough. I need to know also whether the burglary happened. And finally, the alarm, and the alarm in this case is influenced, of course, by the earthquake and by the burglary. However, because we already know John and Mary, let's say that the alarm just sounded off by itself without any earthquake or burglary. Well, if John and Mary called me, it does tell me that these might have happened. So a different order. This is a different order. So before I ordered it E, B, A, M, J. Here I ordered it J, M, B, E, A. And both of them, I use the same domain knowledge. This one is a fully connected, basically 31 parameters. The previous one only 10 or 11. So basically, it means that the ordering of the Bayesian network is very, very important. Or not ordering. Ordering of the nodes, even if you use the same domain knowledge, is very important. Generally speaking, how do you do it? You try to come up with the nodes that have the least dependence, right? So in this case, you know, and burglary and earthquake are not dependent on anything else. They just the triggering events, and then you try to. But sometimes, you know, again, especially if you have a lot of them, there's the limit to how many orders you can test. And so eventually you may not find the optimal network, but at least you can get better than the fully dependent one. Okay, so this is the issue related to Bayesian network ordering of the Bayesian network nodes. Very important. And once you have a network, you can add other nodes. For example, a radio. Let's say we have we want to know whether there was an announcement. Whether there was an announcement on the radio that an earthquake occurred. And of course, in this case, if we know already that earthquake, if we have a node to earthquake, we can add it to R, right? So that's always possible. Bayesian networks are actually, or let's put it this way. until neural network became extremely popular, or actually I would say before. So there was this three waves. Bayesian networks were very popular in the early 2000s or in the late 90s, I would say, in practical application. Then they were, I don't want to say replaced, but superseded by support vector machines and now neural networks. Still, Bayesian networks are very popular and still useful for a lot of different things. They're used in medical diagnostics. So this is a simple example of how to use Bayesian networks to help clinicians make decisions. They're used a lot in computational biology to reason about interactions within biological entities. For example, this is interactions between genes inside the cell, and they're used by a lot of other application areas where you want to do you want to represent things related to joint probability, but you also care about the relationship between them. For example, causality inference using this type of edges. We mentioned Bayesian networks in the context of generating the network, in the context of the meaning of the language. So what do the nodes mean? What do the edges mean? What do the conditional probability tables mean? And these are very important because, as we will see, the major goal of Bayesian networks is to do something called inference. So in this example that I've just shown you, let's say I get a call from Mary. Okay, so this is the only thing I observe. I want to know what's the probability that someone broke into my house, right? Because that's the thing that would make me take action. If someone broke into my house, I have to go there. So for example, if I observe M equals 1 and J equals 0, I want to know what's the probability that someone broke into my house. If I get a call from John and Mary, I want to know what's the probability, right? So this is called inference. If I observe some values and I don't observe the other values, can you tell me what is the probability that some other value is 1? This is called inference, and we'll get to that. That's the main goal of Bayesian networks. So Bayesian networks can deal with cases where you observe a subset of the values and you want to know others. Okay, now you can think of one of these nodes as a classifier, right? As a predictor. So for example, in naive Bayes is also a Bayesian network. If you think about naive Bayes, you can also represent it as a Bayesian network, right? And in naive Bayes, the Bayesian network looks like this. So let's say this is x1, x2, x3, x4, x5, and this is the label y. And we know that everything is independent of everything else if we have the label. Oh, it's actually, right, it's actually the other way around. Right, and the joint is P of x1 given y times P of x2 given y times P of x3 given y, right? This is just a Bayesian network, of course, an extreme one because we assume no conditional dependence between the x's, but this is still a Bayesian network. And in this case, inference would mean that we observe x1 to x5 and we want to know the label. That's a simple inference problem. There are more sophisticated or more problematic inference problems, and we'll get to that. But before we get to the real or the main goal of Bayesian network, there are other things we can do from a Bayesian network that are not related to inference, and this is to find relationships between variables, to find or define relationships between variables. And the most important relationships we can define is something called conditional independence. Conditional independence we already defined several times. We use it in naive Bayes. But for example, we say that x and y are conditionally independent given z if P of x given z equals P of y given z. Of course, we can assume that, but if we have a specific Bayesian network structure, we can ask questions just looking at the network without knowing anything about the probabilities that tell us whether things are conditionally independent or not. Why is this useful? For example, let's say that I have a network and I want to find whether someone has cancer. Okay, so I learned a network of a lot of variables, and one of the nodes is breast cancer, okay? Another node in this network is MRI, okay? So now I want to know whether if breast cancer is independent from MRI given some other nodes, then I don't need to do the MRI because all the information that the MRI will provide me is already given by the other nodes. I can just do this. But if breast cancer is not independent of MRI, I would have to do the MRI in order to fully use the network. So knowing when things are conditionally independent given some other things can tell you what you need to know in order to do the inference, or whether you need to do some very expensive experiment or test or clinical work and so forth. So knowing, even just without the parameters, just looking at the structure, knowing what is independent is a very important thing. And this is something that Bayesian networks are very good at, and they provide information on. It turns out that there's a few rules that you can use to determine, given a Bayesian networks, if things are dependent, conditionally independent, or conditionally independent given something. And this is what we will talk about next. So first of all, any node is independent of all the other nodes given its Markov blanket. What is a Markov blanket? The Markov blanket is defined by all parents, children, and co-parents of children. Okay? So for example, J, if you look at J has one parent, right? A. So A is, and it doesn't have any children or co-parents of children. So J is independent of everything else if we know A. Okay, so if I want to know whether J called me, it's enough for me to know A. I don't care about anything else. But some other nodes have a much more complicated Markov blanket. For example, what is the Markov blanket of B? The Markov blanket of B is all its parents. It doesn't have any parents. All its descendants, A, and co-parents of descendants, in this case, E. Okay, so the Markov blanket of B is E and A. If I know E and A, then B is independent of anything else. So again, that's in terms of inference, that's important because if I want to know B, I just need to know E and A and I can find the value of B. A, on the other hand, is the Markov blanket of A is everything, which could be the case, right? Because everything is either a parent or a child. So this is Markov blanket, but Markov blanket is a very strong assumption. Sometimes two variables can be independent even if we don't have the Markov blanket of one of them. Okay? So there's other rules or additional set of rules that talk about independence, and these are called deseparation rules. Very important rules, a bit confusing initially, but once you get them, easy to work out. Basically, a lot of questions about dependence or independence in Bayesian networks. Okay. Okay. So we say that two variables are deseparated, conditioned on something else. So basically, we say that X and Y are deseparated, conditioned on Z, where Z is a set of other variables, which could include variable or could be an empty set. Okay. So we can have Z as an empty set, which means that X and Y are independent if we don't know anything. Or Z could be some other variables in the network. So we say that X and Y are deseparated given, or we say the two variables are deseparated given Z if they are conditionally independent given Z. Okay, so this is the definition. I didn't tell you how to find it, but this is the definition. This is what we want to find. We want to find cases where, or we want to know whether if I know a subset of variables or whether if I don't know anything, these two are independent. So there's three rules in order to determine if two things are deseparated. In fact, the rules are not talking about deseparation. They are going the other direction. They are talking about whether two nodes are connected. And if they are not, so if two nodes are connected, they are not deseparated. But if you can rule out connections, then they are deseparated. Okay, so that's the idea. If you want to know if two things are conditionally independent, you check whether they are connected. If they are not connected, they are independent. Okay, so what are the three rules? The first rule applies to the case where Z is an empty set. So if Z is an empty set, then X and Y are deconnected if there exists a path between them that does not contain a collider. What does it mean? So let's do. So let's say we have X here and Y here. If there is a path between them, which contains some nodes, or maybe okay, well, that's 1, that's 2, or whatever, and we, of course, and Z is empty, so we don't know anything about nodes in this path, then these two are connected, okay? So this is called a directed path between X and Y. However, if the path has a collider means that within the path, or not if the path, if all paths between them have a collider, this is called a collider. A collider is that one node has 2 incoming edges, 1 from each side, okay? So this is called a collider, this is a collider. If all the paths between X and Y, if there is any, have a collider, then they are not connected. And of course, and Z is empty, okay? So if Z is empty and there is a directed path, they are connected. If there is no directed path, either they're not, I mean, for example, X and Y are like this, there's no path between them, or there is a path that contains a collider, then they are not connected if Z is empty. Okay, so this is the first rule. The second rule is if Z, so the second and third rule are if Z is not empty. Okay, so if X and Y we say are deconnected, if there exists a path between them that does not contain a collider and does not contain any member of Z. Okay, so if there is a directed path between X and Y that does not contain any member that we condition on, they are connected, right? It's similar to the empty set. There is a path, a directed path between them, they are connected. That's easy. Okay, now if Z is not empty, and there is a path between X and Y, but, or let's say, okay, so if Z is not empty, and all paths between X and Y that are directed contain a member of Z, we still say that X and Y are connected if there is a path between them that contain the collider, and Z, basically the variable we condition on, is either the collider or one of its descendants. So let me show you an example. So again, if we have a path between X and Y, let's say that we want to know whether X and Y are independent given M, right? The variable M. So this is X, this is Y. If we know M in a directed path, then they are not connected, okay? So if the path contains one of the members of Z, so in this case, Z equals N, okay, in this setting. So if the path contains a member of Z, then they are not connected. However, if M is a collider, or if M is a descendant of a collider, then they are connected. Okay, so this is the rules. Okay, this is the 3 rules. I'm not going to prove it to you because proving this is not trivial. It's not too hard, but it's not trivial because it requires going through a bunch of cases where you have to, you know, basically it's a somewhat tedious proof. We are going to ask you in the next problem set to do some proofs along that will lead to some of these rules. Not all of them, but we don't want you to do the very long and detailed proof, but you will work on proving some of these things in the next problem set. So the problem set that will be out this week. But generally speaking, I'm not going to prove these rules. I'm just stating them. The good news is that using these rules, and if I give you two random variables, you can use these rules to determine whether nodes in the network are conditionally independent given an empty or a set of nodes that contain some other nodes. Okay, good. So this is this separation. I guess this is not trivial for most of you, at least hopefully, and at least those who haven't seen it. So I think the next thing and I know you asked some question and Daniel is answering them, which is great. The next thing I want to do is let's practice this with some examples. So I'm going to open up two quizzes related to independence, collision, dimensional network. As I always say, and I'm definitely going to say today, this is very early, right? So you just saw this. If you get it, great. If you didn't get it, don't worry. I mean, more practice. This is something we actually practice quite a lot in the problem set. But, you know, the reason why we are doing this as a quiz is because these are things I wanted to show anyway. So let's try it as a quiz and then we'll talk about them in class. Okay, so I'm going to open up two quiz questions. Hopefully people remember the Piazza quizzes. So I have two questions on Bayesian network. Both of them contain figures. So if you don't see the figure, let me know. I think you should see them. And yeah, so let's do this and we'll talk about them and how they relate to the. Okay, so let's start with the first question I asked you. So I presented two Bayesian networks and I asked you whether they are equivalent. Equivalent means that basically these networks have the same assumption. Now, there are different ways to show equivalence. One is something I told you that they represent the same conditional probability. The question is, how do you show it, right? You can show all the pairs or all the subsets and show that they are the same, but that's hard to do. Another way to show equivalence is to show that the joint probability, basically, if I write P of A, B, C, then the factorization, basically the probability of a node given its parent is the same in both networks. So let's see how the factorization works for the second network. Okay, let's start with the second network. So for the second network, right. So if we look at the left network, we have P of A, right? P of B given A, P of C given B and D, and P of D, right? This is just we said that's the joint probability of every node conditioned on its parents. Everybody's okay with me here? Hopefully. Yes, okay. What about the first network? The first the one on the right, we have P of A given B, right? P of B, B doesn't have any incoming edge. Is that true? Yeah. And the rest is the same, right? So P of C given and P of D, right? Everybody sees that. Now, are these two the same? So obviously this is the same, this part here and here and here and here, right? I mean, if we have some probability that we learned and it's, I mean, that's the true probability that it's the same. And now we are left with P of A times P of B given A and P of A given B times P of B. Are these two the same? The answer is yes, right? The chain rule will tell us that both of them are basically P of A, B. Doesn't matter, honestly, which dependency assumption we use. We can always factor P of A and B to P of A times PB of A or P of B given P of A given B. So basically, both networks make the same assumption about independence. In one network, A A is the parent of B, and in one network, B is the parent of A, but both of them are basically the same. The direction of the edge does not necessarily imply causality. It just implies relationships in terms of joint probability distribution. So in this case, the second network is the same. What about the network on the top? The network on the top, and that's actually an example where, right? So we have P of A, P of B given A, and P of C given B. And for the other one, we have P of A, P of B given A and C, P of C. This can cancel out, but these two are not the same. Unless you assume something about the relationship between these, you cannot always say that P of A given P of B given AC times P of C is P of B given A times P of C given B. That's not always true. It's true under some assumptions about the relationship between, but it's not something that based on the probability assumptions you can say, or based on the chain rule, for example, right? If we use the chain rule, or actually the opposite of the chain rule, it will not be something that we can derive unless you make some very strong assumptions that you're not allowed. So in this case, the answer is that
there's a quick question, Ziv, in chat. Someone says, is P of C given B and D equivalent to writing P of C given A, B, and D here?
No. In this case, you're right. I mean, if you knew A, it could lead to some other. I mean, the network does not require you to condition. Or let's put it this way: the network tells you that if you know B, you don't need to know A. You can think about the fact that A, once you know B, in this case, once you know B, then C is independent of A for both of them. So but again, this is just for these variables, right? There could be, I mean, A is just an abstract variable. It could be the case where A is very important and B doesn't help you at all. But for this specific network, that's not true. Okay, let's go to the next question, which actually is using the deseparation idea. So in this case, I asked, okay, sorry about this, right? So the answer in this case is 2, okay? So network 2 is equivalent and network 1 is not equivalent, which a lot of you knew, which is great. I mean, not everybody, but this is just something we introduced. Okay, what about the second question? The second question I asked about deseparation, and yeah, again, this is something we just learned, so it's not trivial. Okay, so the first is whether D, which is here, and S are independent without knowing anything else. In order for them to be, so we say they are independent unless they are separated unless they are connected. If they are separated, then they are independent. When will they be connected? When there is a directed path going from D to S. Otherwise, if there is a path between them that has a collider, because D is empty, they are not connected. In this case, all paths from D to S, right, have a collider. You cannot go from D to S or from S to D without hitting a collider. So the answer is that 1 is true. So basically 1 holds. So A, I guess, is 1 in that case. So this is true, right? D and S are conditionally independent given an empty set, or basically are independent based on this. If we don't know anything, D and S are independent. What about 2? If we know H, then we have a path between them that contains a collider. Or in this case, really, I mean, this is the path between DAH and this is SJH, right? H is a collider in this case. If we know H, we said they are connected. If they are connected, they are not independent. So B is not. So the answer in this case is 1, which the majority is selected. Great. Okay. So this is just a way to use the deseparation. Okay. Now, don't worry if you didn't get it right. As I said, this is extremely quick. We just learned it. And we have lots of, we usually ask related questions in the exam. So this is something you should know eventually, but you have plenty of opportunity. You're going to have in the problem set that we are going to release questions about this separation. And we have a lot of previous exams where you can train and work on it, and, you know, take your time and look again after the class.
Hi, Professor. Can I ask a question?
Sure.
So regarding the previous plot, the graph, the second condition here is that x and y are deconnected given z if there exists a path between them, and the path between them meaning the path between x and y.
Yes.
Yes? Okay. I'm not quite sure about the graph y, x, and
so in this
y
case,
are
x and y are
independent.
DLS, right? This is x and this is y. Oh, I'm not sure, right?
Wait, it's not showing.
Yeah. So in this case, D is X, for example, and S is Y, and H is Z.
Yes.
So this is a collider, right?
Yes.
So if there is a collider and it's part of Z, then they are connected.
Okay.
If they are connected,
Gotcha.
they are not independent.
Yeah, gotcha. Thanks.
Okay, so let's go back to our class, and now let's go to, as I said, what is the real, or not real, but one of the major questions in Bayesian network, and this is inference, basically asking about things that we didn't observe and wanting to know the answer. So once we have the network, and so I must say, for inference, at this stage, we assume that we have the network, we know the nodes, we know the edges, and we know the CPTs. So the network is fully defined. We now want to ask questions about the network. So we want to infer values given that we observed only a subset of the values. For example, I want to know what's the joint probability of a set of values. For example, burglary occurred, earthquake didn't occur, alarm sounded, John called and Mary didn't call. Okay, so in that case, if I have this is a fully observed set of values, right? We observed all 5 variables. We can just look at the network, right? We have, let's say, some probabilities in the network, and we take the joint. And the joint is just the product of each node conditioned on its parent. B and E don't have parents, A has 2, and so forth. And this is the probability. So we have a probability for observing this set is this number here, right? We just go to the network, use the conditional probability tables that we computed. That's pretty easy. But of course, the interesting questions are when we observe only a subset. So when we observe everything, we just plug it in, that's it. But the question is, what do we do about a partial distributions? Or conditional, but let's say partial. So let's say I want to know what's the probability that someone broke into my house if John called me and Mary didn't call me. This is a much more realistic scenario where I really want to use the network, and I'm at work, John called me, Mary didn't. So the thing that I really care about is whether someone broke into my house. Should I go home or not, right? I mean, it's LA, you know, lots of traffic. Going home is not something you want to do in the middle of the workday unless you really need to. So this is the question. Okay. Now I should say conditional probability is usually something pretty hard to do in Bayesian network. Joint is much easier, right? I said that Bayesian network represents the joint probability distribution. So if we have a conditional probability, in this case, we want to compute the probability of B condition on J and not M, we usually turn it into a joint, right? So the probability of A given B and C is just the probability of A, B, C divided by the probability of B and C, which is sum over A, the probability of A, B, and C, right? This is something we discussed many times. Again, just to show you what I've done here. Hopefully everybody is okay. Right, so the probability of P of A condition on B and C equals P of A, B and C over sum over A right. This is the idea that we have for joint. Sorry. So this is basically a simple way to turn a conditional into joints. Okay, that's not fully helpful, but it's helpful. Okay, so how do we? But this is now a partial joint, right? We don't have all of the values in this equation. We only have 3 values, or B is 1, J is 1, and M is 0. How do we compute this probability from the network? We cannot just multiply the probabilities of each node versus its parents because, for example, for J, we don't know the value of its parents. We don't have A in this equation. If we had all of them, we can multiply it, but we don't, right? So what should we do? How do we do inference? How do we learn? How do we determine this joint probability? Anybody? So that's again something pretty simple, although very time consuming. If I want to know, so we know that P of B equals to sum over A, P of AB, right? This is the summation idea. Because B must occur with one of the values of A, so, let's say this is P of B equals 0. So sum over A, P of, right? This is just, so we can do the same thing here, right? We can sum over, if we want to compute a partial joint, we can compute the full joint by summing over all the values of the other variables, right? So in this case, we have 2 missing values. So in this case, we have two missing values, which are in this case A and E. So we can sum over them, right? And this is called enumeration. And we sum over all the instances of all the values we didn't see. And that's how we compute. So for example, if I want to compute the probability of B, J, and not M, I just compute the probability of G, J, and not M, A and E, A and not A and E, A and not E, and not A and not E, right? There's basically 4 possible sets, right? 1, 1, for the missing ones, which are A and D. 0, 0, 1, 1, 0, 1, 1, right? Pretty easy, and we can compute it, and that will give us the joint, the partial joint. Okay, so this is pretty easy. The big problem is, if we have a Bayesian network with 100 variables, we observe 2 and we want to compute the joint probability of 3 of them, then we need 2 to the power of 97 values to compute, right? Everybody sees the problem with, this is called enumeration. Basically, we enumerate, we compute all the missing, or we sum over all the missing possibilities. But this is very, very time consuming, right? If we have, again, even if we have binary variables, 100 nodes, not a huge network, and we only observe 3 and we want to compute the joint of 3 of them, this will be 2 to the power, that's impossible to do. So it's not a good idea, but in small networks, maybe this will be something we can do. Now, there are ways to improve it, and we'll talk about them next time. There's something called reusing calculations and so forth. This is similar to dynamic programming. We'll get to that. But obviously, even that is only going to provide improvement in some cases. But again, as we'll discuss next time, there's no guarantee that whatever reusing of calculation we will do will really provide a solution that is fast, right? The problem with this solution that we mentioned, this enumeration, is that it's exponential, or could be exponential in the number of variables, which is something we cannot tolerate, right? This is inference. This is not learning. So we assume that we know the network. This is just doing inference. So unfortunately, right, the reusing is not. So this is a good idea, but unfortunately, it doesn't solve the problem completely. So what else can we do, or how can we improve this issue? So the answer is, unfortunately, that unlike other cases, for example, in naive Bayes or support vector machines where we use gradient descent and if we make assumptions, in general, doing inference in Bayesian network is NP hard. NP hard, for those who are less familiar with computational complexity, means that unless, or NP is a class of problems that we don't know how to solve in polynomial time, and NP hard means that we can take one of these problems that we know, or that we know that we can show that we can. Or let me take it back. NP means that if we have a solution, we can easily validate that it works in polynomial time. But to find that solution, we don't know how to do it, and it's likely exponential. NP hard problems are problems where we can show that if we know how to solve them, we can solve all of the problems in this NP family. So basically, in order to show that the problem is NP hard, you have to show that if you can solve it, you can solve another problem that is known already to be NP hard. So this is a very big class of problems, and it keeps growing because every time you show that if you can solve one problem using this, that problem becomes NP itself, because if you solve that, you solve others and so forth. So in order to show that, so the goal or the claim is that Bayesian network inference, inferring the values or finding the joint probability, the partial joint, of course, the full joint is easy, but the partial joint in Bayesian networks is NP hard. How do we show that that's the case? In order to do that, we reduce it from a problem called 3SAT. 3SAT is really the canonical NP hard problem. So this is really one of the base problems of this family. And 3SAT is a problem of finding assignments to random variables, which are organized in a set of conjunction. So basically 3 variables, we take the O of them, and then we take the end of all these triplets, okay? So we have, n, let's say we have n variables. We organize them into triplets, okay? So each triplet contains 3 of these variables. A variable can appear in multiple triplets, that's not a problem. And a variable and its negation can appear. So you can have like B or not B. That's a valid. And for each triplet, we have an OR between them. So in order for this to, and we have an AND between all of these triplets. So basically, in order for the statement to be satisfied, in order for this logical form to be 1, we need each of the triplets to have at least one variable that is 1, right? Because this is an AND of all of these triplets. So if we can find, and the question is, can you find assignments to the variables? Because we have the variable and its negation. Can you find an assignment to the variables? For example, A is 1, B is 0, C is 1, D is 0, and so forth, such that this function that we defined is satisfied. This is called 3SAT, or satisfiability problem, okay? And it's known to be an NP hard problem. And what we are going to do is to show that if we know how to do inference in Bayesian network, we can solve 3SAT. If that's the case, then obviously Bayesian network is NP hard, because if we know how to do inference, then we can solve 3SAT, then we solve all the NP problems. Okay, so this is something we will do next time, and I will show you the reduction. I don't want to start, we don't have a lot of time. I want to make one announcement or 2 announcements basically. So tomorrow, as you all know, hopefully, is election day. Some of you, or maybe most of you, have already voted. I think at least nationally, 2/3 of the people already voted. But if you haven't voted, we encourage everybody to vote, and not we but CMU encourages everybody to vote. Because of the vote tomorrow, we decided to postpone the deadline, and this was already announced, but I'm making this announcement, the deadline to problem set 4 to Friday. So you have until Friday to do problem set 4. Problem set 5 is still going to be released tomorrow. Not tomorrow, on Wednesday, right, Daniel? I mean, that's the plan at least. And you will have less than 2 weeks. That was the original plan for, right? And I think we have until Monday. Now, problem set 5 is very different from the other problem sets. First of all, it's the last problem set. After that, we have the exam, and then we let you spend the time on the project. The second thing, it's a shorter problem set. So you will see it will have less questions. There is not going to be any programming as well. So problem set 5, again, I mean, we will still ask theoretical and some practical questions, but it's not going to be, there's not going to be programming, so it should take you less time. And yeah, so that's the plan. Again, if you finished already, you can start. It's going to be released on Wednesday, but for those who haven't, you have until Friday to submit. And that's it. I'll see everybody on Wednesday, and we'll continue to talk about Bayesian network, and we'll start talking about other members of this graphical model family. Bye.